In this video, I want to review the gradient of a function, and the presentation I'm going to give is based on this book, Mathematical Methods for the Physical Sciences by Roel Snyder. All right, to introduce the gradient of a function, we're going to first do a case in 2 dimensions where we have a Cartesian plane with coordinate axes y and x. And on this plane, we're going to define 3 points, A, B, and C, with coordinates x, y, x plus delta x, y, and x plus delta x, y plus delta y. So those are the coordinates of the points A, B, and C. And so the separation between A and B is delta x, and the separation between B and C is delta y. And at each of these points, we're going to evaluate a function, f of x and y, so that f at A is equal to f at x and y. F at B is f at x plus delta x and y. And f at C is f at x plus delta x, y plus delta y. And to motivate the gradient is going to tell us something about how the function f changes locally. And so the change in the function f, delta f, between point C and point A is f at C minus f at A, which we can rewrite as f at C minus f at B plus f at B minus f at A. Notice here I just added and subtracted f of B, so I didn't change anything. Just added 0. Or subtracted 0, however you want to see it. Now the next step will be to expand the function f in a Taylor series about the point A. So I'm going to pick the point f at B and expand it in a Taylor series about the point A. So f at B is f at A plus the partial f partial x evaluated at the point A times delta x, plus the higher order terms. Higher order terms, in other words, terms of order delta x squared or higher. These terms are going to be very small if I pick delta x to be small, and in the limit where delta x goes to 0, these higher order terms are going to vanish because they're of quadratic or higher powers of delta x, which is going to go 0 much faster than this term. And then similarly for the point f at C, that is going to be f at A plus df dx at A times delta x plus and again higher order terms, which are going to vanish in the limit. And from this I can calculate what the difference of f at C minus f at B is and what f at B minus f at A is. So let's evaluate the first one. F at B minus f at A is going to be this expansion, f at A plus partial f partial x evaluated at the point A times delta x minus f at A, this is f at B, minus f at A. The f's at A's cancel, so I just get partial f partial x at A times delta x. This is approximate, and it's going to be exact in the limit where delta x is very small. And I will do the same thing for f at C minus f at B. That will be this expression, f at A plus partial f partial x at A delta x plus partial f partial y at A delta y, plus higher order terms minus f at B, which I have over here in terms of this expansion, f at A plus partial f partial x at a delta x plus the higher order terms. And now if I take the difference, the f at a minus f at a cancels, the df dx will cancel. All I'm left with is this term, which is partial f partial y evaluated at the point a times delta y. So right, this cancels with this cancels with this, and all I'm left with is this term. Now putting this together, this term here and this one, substitute in here in delta f, I get delta f, which is equal to f at c minus f at b, is just partial f partial y evaluated at the point a times delta y plus this term f at b minus f at a, which is over here just partial f partial x at a times delta x. And this, of course, the order of multiplication doesn't matter, so I can rewrite it as delta x delta y as a vector dotted with this vector, which is the vector with the partial derivatives. If I do that, notice that I do the dot products, this times this plus this times that, which is what I have over here. And we give this vector here with the vector of partial derivatives, we give this a name. So we define grad f in 2 dimensions and in Cartesian coordinates. This is a definition in 2D and Cartesian. Now what we're going to see is that grad f is a vector, and this vector doesn't really depend on the coordinate representation. So we can represent it in spherical coordinates, cylindrical coordinates. It's a proper vector, and so what it looks like will depend on what kind of coordinate systems we use. It's going to be simplest if we're using Cartesian coordinates, in which case the gradient, its components, will just be the simple partial derivatives with respect to x and y. And you can generalize the argument I just did to other dimensions, and in fact in 3 dimensions we would have the following: df dx, df dy, and df dz. You can go through the same kind of reasoning I just did for the 2-dimensional case, and you'll get the same kind of thing in 3D Cartesian coordinates. Later we'll see how to express a gradient in spherical coordinates, which are useful for doing the geosciences where we're dealing with the Earth, which is nearly a perfect sphere. So I think it's useful now to do an example of calculating the gradient. So calculate So this function is x times e to the minus y times sine of z, and we want to calculate its gradient. So grad f is going to be equal to partial f partial x, partial f partial y, partial f partial z. We'll have 3 components. And partial f partial x, well, when I take the partial derivative, y and z are treated as constants, and so derivative with respect to x is just going to give me back the constant, which is e to the minus y sine of z. And then partial f partial y, now x and z are like constants, so I'll just get the derivative of e to the minus y, which is just minus e to the minus y times the constant. So that will be x minus e to the minus y sine of z. The minus here comes from the chain rule when you do the derivative of y on e to the minus y. And finally, the partial derivative with respect to z. now x and y are like constants, and the derivative of sine of z is just cosine of z. And so this is an example of computing the gradient of this particular function. And if we want to know what's the gradient at a particular point in space, we would pick some coordinates x, y, z and stick them into these components, and then we'd get the size and direction of the gradient grad f. So to see what the meaning of the gradient is, let's go back to our 2D example, y and x, and suppose we have contours of constant f. And we pick delta r to be aligned with the contour. So suppose this is the point C and the point A, and delta r is equal to C minus A. Then delta f, which is f at C minus f at A, is going to be 0 because we're on the contour of constant f. F at C is equal to f at A. But we can also use our expression for what delta f is using the gradient. So we also have delta f is equal to delta r dotted with grad f. Putting these two together, we know that delta r dotted with grad f is equal to 0, which means that delta r is perpendicular to grad f. So grad f is pointing in the direction perpendicular to a line of constant f. And in fact, if we use the expression for the dot product, delta r dotted with grad f can be written as the magnitude of delta r times the magnitude of grad f times the cosine of the angle between the vector delta r and the vector grad f. We see that this will be a maximum when cos theta is 1. And cos theta equals 1 implies that theta equals 0, which implies that delta r is parallel to grad f. So that means that grad f is pointing in the direction of maximum increase of f. So delta r, grad f points. So it points in the direction of maximum increase in f. So if you're a hiker and you want to go take the shortest distance to the top of the mountain, you can go in the direction of the gradient, because it's pointing in the direction in which the hill is steepest, in the direction of maximum increase. And that means that the size of grad f is equal to So if you pick delta r in the direction in which f is increasing most rapidly, then the magnitude of the gradient can be given by the change in f divided by the size of the delta r vector. So I think now we're ready to summarize the main results. So the gradient of f is perpendicular to a surface f equals a constant. In 3D, f is constant will be a surface. In 2D, f is a constant will be a contour. 2. The gradient points in the direction of maximum increase of f. And 3. So the magnitude of the gradient is equal to the change in f in the direction of largest increase divided by the distance delta r in that direction. So it looks in this direction, it just looks just like a regular derivative, provided we pick a direction when we do the derivative in which f increases rapidly. So the gradient is kind of a generalization to multivariate function of the derivative that we know from regular calculus. So an important example of the gradient in fluid mechanics is the gradient as the pressure force, right? The pressure force, an example of the gradient is the pressure force in fluid mechanics, which points down gradient from high pressure to low pressure. So F pressure is equal to minus the gradient of the pressure. So the pressure is just a scalar function, but it's a function that varies in space, and the pressure force is going to be equal to, in magnitude, to the gradient, the magnitude of the gradient of the pressure field, but it will be pointing from regions of high to low pressure, so we need the minus. Another example is getting Newton's law from energy conservation. So the total energy, 1/2 m v squared plus the potential energy V of r is equal to the total energy E. This is the kinetic energy. This is the potential energy. This is the total energy. And suppose that there's no dissipation, so suppose that the total energy is conserved. No dissipation. Then the time rate of change of E is 0. So let's compute the time rate of change of the kinetic energy. d by dt, where V is equal to the magnitude of the vector B, which is equal to the square root of V dotted with V. So I can rewrite this expression as d by dt of 1/2 m V dotted with V, because V dotted with V is V squared, is the magnitude squared. Now if I use the product rule on this, I'll get 1/2 m V times dV dt plus, that's the derivative of the second times the first plus the derivative of the first dotted with V, which is just m times V dotted with dV dt. So this is the time rate of change of the kinetic energy, is the velocity dotted with the time derivative of the velocity. And now we're going to take the time rate of change of the potential energy. Okay, we're going to take the time derivative of the potential energy, d by dt. And here, this is the total time derivative, and so V is implicitly a function of time through the fact that the position vector can be moving in space. So this becomes the limit as delta t goes to 0 where delta r is the vector difference between r at t plus delta t and r at t. And if we substitute this into the difference of v in the numerator, we get a limit and then we use the fact that the limit of delta r vector over delta t is the definition of the velocity, right? V. And so this becomes, where the capital V without the arrow on it is the potential energy function, and the little v with the arrow is the velocity vector. Now putting together the time rate of change of the potential energy with the time rate of change of the kinetic energy, we get d by dt is the time rate of change of E, the total energy, which we know is 0. Therefore, d by dt and now we can pull out the common v vector, which is dotted into the result. Now we didn't specify how this point r here moves in time. It can move in any old way. So that means this velocity vector is an arbitrary velocity vector. And so if this dot product of this arbitrary velocity vector with this vector here, which is the gradient of the potential plus m times the acceleration, if this is going to be 0 for any v, then the only way this can happen is if the quantity in parentheses is itself equal to 0. So that means that and now if we identify the force as being negative of the gradient of the potential energy function, then we'll get Newton's law. So if we identify the force to be minus grad v, then which is Newton's second law.